Good evening, everyone, and I welcome you all to today's live session for the course Elements of Mechanical Vibration. So, we are into the week 7 live session, and I'm Rashia Ranjan, NPTEL PMRF TA, the PMRF scholar in the Department of Mechanical Engineering, IIT Patna. So, we have already completed 6 live sessions as of today for this course, and we have tried solving the problems which were related to the theory that you people have been taught during the lectures so that it will be helpful for you to solve the assignment problems. And I hope that you people are enjoying. So we will be discussing the questions directly. So first we'll come on to the first question, which is more about degrees of freedom. Because till now we were discussing about systems which were having 1 degree of freedom, or we can say systems wherein we were modeling it as a 1 degree of freedom system. Like, for example, if you remember, we had a cantilever beam. So, we had a cantilever beam, and then a force was being applied on it, and then it was deforming by some amount, it's bending like this. So essentially, this is actually a continuous system, and we know that a continuous system has infinite degrees of freedom because it has infinite mass points. But we were modeling it as a 1 degree of freedom system, right? We considered it as a mass connected by a spring, something like this, right? And then we were applying a force P, and then the deformation that the spring was going on was modeled as delta, which was the deflection of the beam. So what were we doing? We were modeling the system by a 1 degree of freedom system, by the use of a 1 degree of freedom system, right? But now, every time modeling any system as a 1 degree of freedom system is not a very good idea, though it is one of the basic and one of the easiest way, but it is not always true, and it does not always give accurate results that we require. So introducing multi-degree of freedom system in order to model a particular continuous system gives us better accuracy for the system. Okay. So for example, for cantilever beam only, instead of modeling it as a 1 degree of freedom as one mass point, what we can do is we can divide it into 4 mass points and then connect it by a spring. So it will become a 4 degree of freedom system. And the final displacement of the last mass can be considered as the deflection of the beam at the point where the load P is applied. Okay, so first we'll study the question which says that consider a mechanical system consisting of 3 identical point masses M, each constrained to move horizontally only. Okay, the masses are connected by 2 identical linear springs of stiffness K. So we have 3 masses, something like this, and then we have 3 masses. One, two, and three. We have 3 masses. Like this. Each mass is M, identical, and then we have 2 springs of stiffness K. Determine the degree of freedom for the system. So we need to determine the degree of freedom of the system. So over here, if you look, then we have 3 masses, correct? And we have two springs. Each mass is going to have a deformation x1, x2, and x3, right? And these deformations are actually not same, right? These are three different deformations. Now, we need to find out the degree of freedom. I don't have any idea that how many equations should I write, how many independent coordinates are required and everything. I don't know anything. So there is a basic rule, okay, which says that the degrees of freedom is equal to number of mass multiplied by number of possible motion of each mass. Okay. So over here, if you'll see, it is written in the question that each mass is constrained to move horizontally only. So every mass is having only one possible motion. Correct? Every mass is having one possible motion, and then there are three masses like this. So essentially the degree of freedom are going to be 3 into 1, 3. However, as you can see in the later part of the question, it says that a rigid rod is used to connect the first two masses. Is the degree of freedom changed or remain the same? Now what we have done is, in this case, when both the springs are not in any stretched or compressed state, they are simply in the rest. Okay. What happens is that we add a rod over here. Okay. Like this. Now this is a rigid rod. Okay. So what is going to happen? This rod is not going to let the first two masses go away from each other or come close to each other. Both the masses will remain at the same position with respect to each other. Correct? You can say that now it acts as a single mass. You can consider it like that because it behaves like that only. Both of them will be together. It will oscillate something like this, like a single mass. Okay. So if I want to use this equation, what I can do is I can reduce the number of masses to 2. Okay. Because although there are three masses only, there are not two masses, there are three masses, but the first two masses are connected by a rigid rod. Okay, now because of that rigid rod, these two masses are not going to show any relative motion with respect to each other. They will go forward or backward with the same velocity and the same position it is going to attain. Alright, so essentially there are only two mass points for which I need to find out the x1 and x2. Correct? So I can use that equation in that way. But then there is one more way of defining the degrees of freedom. Okay, I'll add one more slide which says that degree of freedom is equal to number of mass into possible motion minus number of independent constraint. Okay, now what does this say? This basically means that we find the number of possible motions. For now, we don't consider any kind of constraint or any kind of restriction that we have given to the system. And then we subtract the number of constraint that we have imposed on the system. Like for example, if I take this mass only, which is on a surface like this. Okay. Now, when I say that I have constrained it to move horizontally, so I write its degree of freedom is 1. But if I think physically, a mass in space, okay, how many motions it can have, how many degrees of freedom it can have. So, in a three-dimensional system in which we live, a mass can have 6 degrees of freedom, which are the translation motion along the three axes and the rotation along the three axes, right? Something like this. We have the three coordinates x, y, and z. So we are going to have any mass can have 6 degrees of freedom. Translation along x, translation along y, translation along z, and then we have a rotation along x, rotation around y, rotation around z. These are the 6 possible degrees of freedom. Now this mass can have 6 degrees of freedom. So if I need to find out its degree of freedom, it is going to be 6, 1 into number of possible motions. Now I have to minus the number of constraints, right? So the first constraint I have constrained it in the z direction, and then I have constrained it in the y direction, which is two translations are gone. Plus I have constrained it to not rotate about any of the I have constrained it to not rotate about any of the axis. Okay. Plus I have constrained it to not rotate about any of the axis. So then we are going to have minus 3. So the total degrees of freedom is 1. Right? But this time we can actually think about the constraint. See, previously when we were using this equation, what were we doing? We were just multiplying the number of mass with the possible motion. But here, when we were applying a rigid rod between the first two masses, we were now considering it as a single mass. However, there were two masses. But if we consider the two masses, but then it is going to give us a degree of freedom of 3, which is not true for this case. We have because we have restricted any kind of relative motion between the first two masses. Correct? So now, if I talk about this equation, wherein we can find out the possible motion and then subtract the number of independent constraint. So now if I try to use this equation in order to find out the degrees of freedom of the system after the rod is introduced, the degrees of freedom is equal to number of masses, which are 3, possible motion, which is 1 because we have constrained it to move only in the horizontal direction, and minus 1 because we have one constraint wherein we have stopped the relative motion between the first two masses. This is because constrained the relative motion between the first two masses. So essentially the degree of freedom is nothing but 2. I hope this is clear. The question is, why do we need to even think about the degrees of freedom? See, when we are modeling a system, it is very important that we know about the degrees of freedom. Because on the basis of degree of freedom only, we are going to find out the number of equations. If we are having a 1 degree of freedom system, there is going to be one equation. If we are having a 2 degrees of freedom system, we are going to have two equations. If we are going to have a 3 degrees of freedom system, we are going to have three equations, right? So depending upon the complexity of the problem, we can choose the how many degrees of freedom that we want in our system, how many independent coordinates that I want in my system. And once I've decided that, I can find out the equation. Now, after I find out the equation, then I can solve it to get the solution. Okay. But the knowledge of degree of freedom is very important. Like for example, when I had these two masses, M1 and M2, how would I know that how many degrees of freedom are there? Right. So it is very simple that the thing that we need to keep in our mind is that every mass is going to introduce a degrees of freedom. Okay, every mass is going to introduce a degree of freedom. So if there are two masses, there's going to be 2 degrees of freedom until and unless there is no kind of a constraint present. Okay, if there is any kind of a constraint, then this 2 degree of freedom system will become a 1 degree of freedom system. Okay, I hope that is clear. Similarly, for the question that we solved over here, we had a 3 degree of freedom system and then we solved it and we got only 2 degrees of freedom because of the constraint that both the masses were joined by a rigid rod. Okay, I hope this is clear. Okay, so the answer is 2. Now, coming on to question number 2, wherein we have to derive the equation of motion of the given system. If you look over here, we have a system with base excitation. We have already derived the equation of motion and solved various questions for a single degree of freedom system with base excitation, right? And then we could also use those solution to find out how the system is going to behave. Now in this case, we have 2 degree of freedom system. So we have two independent coordinates, right? So we have to find out the equation of motion. Earlier it was easy for a 1 degree of freedom system because we had only one coordinate that we need to take care of, right? Now over here, if you look closely, it is essentially having three things that needs to be taken care of. For the first two are the degrees of freedom, x1 and x2, and the second one is yt, which is the displacement of the base, you can say. Okay, the base is not having force excitation, rather it is having displacement excitation. So it is also acting as a degree of freedom. But the thing is that yt is known to us because it's the input. If it would have not been known to us, it would become a 3 degree of freedom system. But here it is known to us, so we need to find out the values of x1 and x2 only. Okay. So to find out the equation of motion, the best way is either we had the energy method, then we had the virtual work method, and then we were also using force balance method. So depending upon what kind of a situation and what kind of a system it is preferable to use that any of the three methods to find out the equation of motion. Usually, when a system is of this type, wherein we have excitation involved in the system, we prefer using the force balance method, right? Because if we talk about energy method, therein we consider only the conservative energy, right? For a non-conservative system, then we have the modified Rayleigh dissipative potential, but we don't know how to deal with forces. However, we have Q1 and Q2 that we introduce in case of a Lagrange equation. So basically, we were finding out the total energy, right? We were differentiating it, but it was applicable only for conservative system. When we come to non-conservative system, we were using Lagrange equation, right? Now Lagrange equation was again used for a conservative system. For non-conservative system, we had to define the Rayleigh dissipative potential, and then we had principal forces Q1 and Q2 that we can use in order to include the effect of any kind of a forcing. But over here, we don't have the direct forcing, right? F1 or F2. Instead, we have the displacement input. So we'll prefer using the force balance method over here. So for the mass M2, if I make the free body diagram, if it is getting displaced by x2 amount in the upward direction, the inertia force is going to act in the downward direction. Okay. Then, since the mass is going upward, the spring and dashpot are going to apply a force in the downward direction. So we'll have C2. Now, if you look over here, this spring is between two masses, which are both are getting displaced, right? So the force that this spring is going to apply will depend upon the relative displacement between x1 and x2, right? The relative displacement between x1 and x2. So in this case, C2 into x2 minus x1 we are going to write. Okay, we are assuming that x2 is greater than x1. Then we also have a spring force. Okay, here it should be dot, and then we are going to have K2 x2 minus x1. Okay, these are the only forces that will act on M2. So for M2, it should be 2. Equation of motion will be M2 x2 double dot plus C2 x2 dot minus x1 dot plus K2 x2 minus x1, and it is equal to 0. So this is the equation for the mass 2. Now when we come on mass 1, M1, it is getting displaced in the above direction by as x1t. So inertia force will act in the downward direction as m1 x1 double dot. Other than that, we have c1 x1 dot, we have k1 x1. Now the above spring and dashpot, they are also going to apply the force. So considering that K2 is in compression, it will apply a force in the downward direction. But now in the opposite side. See, if you look over on the mass M2, we have K2 into x2 minus x1 in the downward direction. Okay. So it will get applied in the upward direction for mass M1. Okay. If I take the negative of it and it pointed downwards, it will simply become K2 into x1 minus x2. Okay, this is very simple. So here we are going to have C1 x1 dot minus x2 dot and K1 x1 minus x2. So these are all the forces. Now apart from that, there is one more thing that we missed over here. See, all these equations are true, not this actually, this both are true for yt is equals to 0. But here we have yt, we have a relative displacement of the spring K1 and dashpot C1 as well. This is because though mass m1 is moving by amount x1, the base to which these spring and dashpot are connected are also moving by the amount yt, right? So we have to write this as k1 x1 minus yt and c1 into x1 dot into yt dot. Okay, I hope this is clear. So using this, the equation of motion becomes m1 x1 double dot plus c x1 dot minus yt dot plus k1 x1 minus yt plus c1 x1 dot minus x2 dot plus k1 x1 minus x2 is equal to 0. Now we try for multi-degree of freedom system to generalize the equation, right? Like for a single degree of freedom system, we had the equation like mx double dot plus cx dot plus kx is equals to 0. Correct? We try that for multi-degree of freedom system, we can still generalize the equation and write it in this form. The only difference is going to be that now for multi-degree of freedom system, this m, n, x and c are going to be matrices. So it will be something of the type m x double dot plus c x dot plus kx is equals to 0. something of this type. Now this x is going to be nothing but x1 and x2, right? So in order to convert these two equations in that form, what do we have to do? We have to write these equations in the form wherein we can change it something like this. Here everything is fine because we have everything in terms of x1 and x2. But over here we have yt and y dot of t as well, which we need to work on in order to get the equation in that form. So what we can do is we can just take the terms which are related to y on the right hand side, okay, and then we can write it in terms of the generalized force. So if I use m1 x1 double dot plus c1 into x1 dot plus k1 into x plus k2 x1 minus x2, okay, I should write c first, c c2 x1 dot minus x2 dot plus k2 x1 minus x2 is going to be equal to what? It is going to be equal to c1 y dot t plus k1 into y of t. Now you can look over here and see that the equation on the left hand side is dependent on only x1 and x2, and on the right hand side we have the terms related to y, which we can treat as the generalized forcing. Okay, so we can write it in a way that m1 x1 double dot plus c1 plus c2 x1 dot minus c2 x2 dot plus k1 plus k2 x1 minus k2 x2 is equals to c1 y dot of t plus k y of t k1. And then the first equation was m2 x2 double dot plus c2 x2 dot minus c2 x1 dot plus k2 x2 minus k2 x1 is equals to 0. Now I can try and write it in the matrix form, right? So what I can do is I can make the mass matrix as m1 0 0 m2 into x1 double dot x2 double dot plus c1 plus c2 minus c2 minus c2 and c2 into x1 dot x2 dot, right, plus k1 plus k2 minus k2 minus k2 k2, and then we are going to have x1 x2 is equal to 0 c1y dot t plus k1 y of t. Okay, no, it should be 0. like this. So this is going to be the equation of motion in the matrix form. We can write it in a generalized way as m x double dot plus c x dot plus k x is equals to f. I hope this is clear. So the second question was about finding out the equation of motion on the system, and we have successfully found out the equation of motion. Now we'll go to question number 3. Yeah, okay. So we have to derive the equation of motion and natural frequencies of the given system. See, but this system that we are looking over here is essentially a 2 degree of freedom system, right? If you can see, there are two masses. So firstly, if there are two masses, it means it's a 2 degree of freedom system. Then we have to look about the constraint. So every mass in free space can have 6 degrees of freedom. Over here, the mass m is what? It is constrained to move only in one direction. So mass m is going to have 1 degree of freedom. And then mass 2 is going to have, now if you see over here, mass 2 is actually oscillating, right, in the xy plane. But this oscillation, which is for a pendulum, the x and y coordinates can be linked by the relation x square plus y square is equals to L square, right? So the mass m2 is going to have 1 degrees of freedom. So total degrees of freedom is going to be 2. If there would have been a kind of constraint for connecting M and M2 in such a way that the position of M can be found out with respect to M2 or vice versa, then it could be a 1 degree of freedom system, right? But here there is no such constraint of that type. So we are going to have only 2 degree of freedom. So for a 2 degree of freedom system, we need to find out the equation. Now for a 2 degree of freedom system, we are going to have two equations. We need to find out the two coordinates as it is given in the question. One coordinate is x1 and the other coordinate is x2. However, what we can do is we can consider the coordinate theta as well. Both are going to work. So maybe I'll find the equation of motion using both. Like one will be using x1 and theta and the second one will be using x1 and x2. Okay. So first, if we'll write the force balance or the free body diagram for mass m. For mass m, it is displaced in this direction by the amount x1. So both the springs are going to apply force in the left direction. Here in this direction it is going to be k2 x1. In this direction it is going to be k1 x1. Other than that, because of the pendulum, a force will be applied because of the thread or the rod which is connecting the pendulum bob with the mass m, right? Now that force, we know that for a pendulum like this, we have mg. So a force is going to be something like this, which is going to be P. So what is going to be the value of P? So we can break mg in two parts. One will be in this direction of P, other will be perpendicular. And this angle is theta as it is given in the question. So mg in that direction is going to be what? It is going to be mg cos theta. So P is going to be equal to mg cos theta. Other than that, mg, this P is acting in which direction? For the mass, P is acting in this direction. with angle theta. Since M is constrained to move in only horizontal direction, so we'll consider the horizontal component of P, okay, which is going to be P into sine theta. In which direction? In this direction. P into sine theta. And then we can consider the inertia force in this direction. So the equation of motion for this mass is going to be m1 x1 double dot plus k1 x1 plus k2 x1 minus p sine theta is equal to 0. This is the first equation, and here we have two coordinates x1 and theta. Now when we come to the bob, so what is happening with the bob? It is rotating like this with the amount theta. So we know that for this kind of a system, we can write the equation for a pendulum as m L square theta double dot plus mg L sine theta is equals to 0. Right? mg L sine theta is equals to 0. So these are the equations. Now if we consider that theta is small, then sine theta is nearly equal to theta. Sine theta is nearly equal to theta. And cos theta is, if sine theta is nearly equal to theta, cos theta is what? 1. So we have the final equations as m1 x1 double dot plus k1 plus k2 x1 minus mg theta is equals to 0, and m L theta double dot plus mg theta is equals to 0. So these are the first set of equations, which is in terms of theta. But we can also use the coordinate x2 instead of theta in order to find out the equation. Okay, x2 is what? See, if at the reference the position of m such that both the springs are not stretched, okay, whatever we get the position, that position, from there the displacement of m is considered as x1, and then the deflection of the bob, which would actually contain x1 as well as the change of theta, from that position is x2. So essentially, if mass, maybe we can just use the reference over here only. This was the initial reference. Now the mass has moved like this. This is x1, and then there is this bob where this is theta. So this is x2, which is equal to x1 plus L sine theta. X2, which is equal to x1 plus L sine theta. Now if we use this equation in order to find out the solution now, so what do we have? We have m1 x1 double dot plus k1 plus k2 x1, and the third term was what? It was related to the force, which was minus of p sine theta. Now we have to convert this sine theta or the term related to theta into x2 or x1. So for a small angle theta, what do we have? See, if this is theta, okay, initially the position was here, from where the position of bob is x2, and the position of mass, which is over here, is what? x1. So this is what? x2 minus x1, right? And this is what? L. So we know that sine theta is nothing but perpendicular by hypotenuse, which is x2 minus x1 by L, right? So we can replace that over here by sine theta. And so we get the new equation in terms of x2 as m1 x1 double dot k1 plus k2 x1 minus p into x2 minus x1 divided by L is equals to 0, right? Similarly, if we talk about the bob, now we have x2 as the displacement of bob, and then we have a force that is acting over here, right? But this time, this force is in this direction, but we are concerned about the force component of this force P in the horizontal direction. So if this is theta, this is 90 or 180 minus theta, right? And then if we have, no, not 180, it should be 90 minus theta because this is a right angle triangle, 90 minus theta. So we'll have P into cos of 90 minus theta, which will be something like m2 x2 double dot, and then we'll have plus mg x2 minus x1 by L is equal to 0, which is because of the sine theta, right? We'll have P in this component. So that is how it is going to be. Again, we have considered theta is small, so definitely the cos component is going to be 1. These are going to be the two new equations. Now we are supposed to find out the natural frequencies of the given system. How do we find the natural frequency? See, we have two equations, correct? Now we need to use these two equations in order to find out the natural frequencies. So there are going to be two natural frequencies, definitely. Since we have two mass, there are going to be two natural frequencies. What we can do is for now assume that x1 can be written as x1 cos of omega t plus phi, and then x2 can be written as x2 cos of omega t plus phi. We're just assuming the solution is of this form. Then what we can do is we can differentiate this to find out x1 dot and double dots. And when we put it in the equation, main equation, what do we get? We get minus m1 omega square plus k1 plus k2 okay, k1 plus k2 plus, see what is P? P is essentially nothing but mg into cos theta, right? And since we are assuming theta is small, cos theta is going to be 1. So P can be replaced simply by mg, right? It can be replaced simply by mg. So we are going to have with plus mg by L, this whole into x1 minus mg by L into x2 is equals to 0. Okay, because after this what we are going to have, see, after this equation we are going to have everything multiplied with cos omega t plus phi. So cos omega t plus phi is not always equal to 0, so we make this term equal to 0. Second term is going to be minus of m2 omega square with x1, and then we'll have minus of minus, yeah, with a minus mg by L into, no, here we are going to have plus into x2 minus mg L by into x1, 0. So by equating the coefficients equal to 0, we get these two equations. Now using these two equations, what we can do is we can write it in a matrix form, right? We can write it in a form like minus of m1 omega square plus k1 plus k2 plus mg by L. It should be m2g, right? M1 and m2. Let me see. By L minus m2g by L minus m2g by L into minus of m omega square plus m2g by L. This whole into x1, x2 is equal to 0. Again, this cannot be equal to 0. So the determinant of this could be equated to 0. So we find out the determinant. What do we do is we write minus of m1 omega square plus k1 plus k2 plus m2g by L minus m2g by L minus m2g by L minus m omega square plus m2g by L, this equal to 0. When we'll equate it to this and solve it, we'll get a polynomial with a power of omega as 4. And when we'll solve it, we'll get 4 values of omega, among which only the positive values will be considered, and those two values are going to give the values of the natural frequency. So I'm not going into it since it's a very mathematically rigorous process and I have to take other questions as well. So you people can do it on your own also. You just have to solve the polynomial, nothing else. So question number 4, wherein we have to find out the natural frequencies and mode shares of the system shown in figure below. So this question I've taken up because in order to give an idea about how mode shapes work and how do we compute it, and why is it even required? I mean, why are we even concerned about it? Because for a linear system we were concerned about resonance. We wanted to avoid resonance. We wanted to know that what is the natural frequency of the system. Over here, since we have 2 degrees of freedom system, we'll have two natural frequencies. And what is going to be the behavior of the system when any of the two natural frequencies are used to excite the system? And by finding out the mode shapes, we can know that giving what initial condition to the system would excite any of the two modes of the system. Okay, so for this system, again, it's a 2 degree of freedom system. We'll write the force balance to get the equation of motion. So m1 is getting displaced by x1 of t, which will cause the inertia force m1 x1 double dot, a spring force k1 x1. Other than that, there's going to be another spring force which will be because of the relative displacement between x1 and x2, and it will be written as k2 x1 minus x2. For now, we can consider k1 is equals to k2 is equals to k3 is equals to k. Okay, so just replace this And then mass also we have to consider as equal only, K and K. Simple. We'll get the equation m1x1 double dot plus k1x1 plus k, okay, have to write k only, k x1 minus x2 is equals to 0, or m1x1 double dot plus 2kx1 minus kx2 is equals to 0. This is going to be our first equation. Force balance for the second one, m2, what do we have? It is getting displaced in this direction, so inertia force as m2x2 double dot then a spring force which will be k x2 minus x1. Again, I would like to tell that k x2 minus x1 in the above direction, because if you look for mass m1, we have a force k x1 minus x2 which is acting in the upward direction. So its reaction is going to be in the downward direction, which will be equal to k x1 minus x2. So if I'll take the negative and change the sign, it will go in the upward direction by the amount k x2 minus x1, and a spring force as k x2. So this will give m2 x2 double dot plus k x2 minus x1 plus k x2 is equals to 0, or m2 x2 double dot minus k x1 plus 2 kx2 is equals to 0. So this is going to be our second equation. Now what we can do is we can assume that x1 is written as x1 cos of omega t plus phi, and x2 is x2 cos of omega t plus phi. Both are oscillating with a frequency omega, and the phase difference is phi for both of them. The only difference is the amplitude, which is capital X1. Now we can use these two to find out the second differential of x1 and x2 like this. We'll find out and put all this in, putting in equation 1 and 2 gives. What does it give to us? So it is going to give us the equation in the form minus m omega square plus 2k x1 minus kx2 is equals to 0, and we are going to have minus kx1 plus minus m omega square plus 2k x2 is equals to 0. Let me check once. Minus m omega square plus 2k minus k minus k into x2. Okay, it should be x1. Yeah, that's fine. Yeah, minus of kx1 and then m2 with omega square in negative direction plus 2k. Yeah, okay. This was going to be equal to 0. Now again, if I write it in the matrix form and then find out the determinant, what do we get? So basically, we'll have minus k minus m omega square plus 2k x1 x2 is equal to 0 0. This cannot be equal to 0. So definitely determinant of plus 2k minus k minus m omega square plus 2k will be equal to 0. This implies minus m omega square plus 2k whole square minus k square is equal to 0. If I'll break it, m square omega to the power 4 plus 4 k to the power 4, sorry, k to the power square, k square minus 4 m k omega square minus k square is equals to 0. This will give us the equation m square omega to the power 4 minus 3k square, sorry, 4 plus 3k square minus 4 mk omega square is equals to 0. So this is a polynomial with the order 4. So what we can do is, for now we can assume that omega square is equals to omega dash. Then it will be a quadratic equation, and for the quadratic equation we know how to find out the roots, because the roots are only going to give us the natural frequencies of the system. So if we use that, let omega dash is equals to omega square. So our equation becomes m square omega square minus 4 mk omega plus 3k square is equals to 0. M square omega square 3k square minus 4 mk. Yes, now the value of omega dash is going to be minus b plus minus under root of b square minus 4, so 3 was a 12, m square k square divided by twice of m square, right? So we'll have 4mk plus minus, so 16 minus 12 is 4 and under root of 4 is 2, twice of mk by 2m square. So we'll have omega dash 1 is going to be 4 plus 2, 6, 6 divided by 2 is 3, k by m, and omega dash 2 is k by m. So omega 1 is under root 3k by m. We are considering only the positive values because frequency cannot be negative. Or maybe I should write it in another way. It will be confusing actually, because this should be omega 2 and omega 1, because we always find out the natural frequency as the first and second natural frequency, and the first natural frequency is the one which is lesser, second natural frequency is one that is higher. So that is why I've given 1 and 2. I can write it as 2 and 1 also. In that case also the lower one is going to be the first natural frequency, but it is preferable to write omega 1 as the lowest one because it was easier to relate. It helps in intuitive understanding. So omega 1 is going to be under root k by m, and omega 2 is going to be under root 3k by m. So these are what? These are our natural frequencies. There are two natural frequencies. Now, we need to find out the mode shapes. So in order to find out the mode shapes, if you remember that in the lecture it was taught, this equation was taught. So I'm not going into how this equation was uh, obtained. I'll just write it. So there was equation like wherein we defined R1 ratio with the first one, which is along the first mode, as x2 at 1 divided by x1 at 1, which was minus of m omega 1 square plus 2k by k. Now if you put the value of omega 1 square over here, you will see that omega 1 square, which is k by m will get cancelled. So we are going to have minus k plus 2k, and eventually it will give us a value of 1. Okay. R2, no, R1, R2 of 1 is going to be x2 at 2, x1 at 2, which is minus m omega 2 square plus 2k by k. Now omega 2 is under root 3k by m. So it is going to be minus 3k plus 2k, which is going to give us minus 1. Okay. So over here you can see is that when the system is excited at the first frequency or at the first frequency, first natural frequency, x1 and x2 are going to have a ratio of 1, which means that x1 and x2 are going to have the same values and the ratio is 1. The direction is also the same. But for the second frequency, the x1 and x2 are going to have a ratio of 1. Absolute value is going to have a ratio of 1, but the direction is opposite. So if x1 is in the positive direction, x2 is going to be in the negative direction. While for the first mode, both are going to be in the same direction. So we can write for the first mode, the solution as x1 of t, which is a vector, as what? It's x1 of 1 cos of omega 1, or we can simply write it as under root omega t cos omega t plus phi plus x1 of 1 cos of omega t plus phi. For the second mode, x2 of t we can write as x1 of 2 cos of 3k by m under root t plus phi. Here it is going to be a minus, because if you look over here, the ratio is what? Minus 1. So x2 of 2 can be written as minus of x1 of 2 minus x1 of 2 cos of omega t plus phi. Okay, I hope this is clear. So these are going to be the way, the modes of the equation of the modes of when the system is excited at the first natural frequency or the second natural frequency. If we would like to visually understand that what is happening, visually if we would like to understand, I'll just explain it over here. I'll not explain in the other questions. So visually if I would like to understand, so let us try, we'll make a reference. Then we'll have a spring, mass 1, another spring, mass 2, another spring, and then again a fixed line. Okay, something like this. So this is the system in the neutral state. Okay, it is having no actuation, it is in the equilibrium state. If I draw the reference line over here for mass m1, we have the reference line like this. Mass m2, we have the reference line like this. Okay, now if I would like to plot it, I would like to plot. So we'll first plot the mode for the first frequency, first natural frequency. So if you remember, the ratio was 1, which means if x1 was like going up by some amount, x2 was also going up by the same amount. So if the mass m1 is going up, mass m2 is also going up by the same amount. If mass m1 is going down, mass m2 is also going down to the reference. And the amount is also the same. Amount is going to be the same. Okay, so if this is x1, this is x1, this is x1, this is x1. This is for the first mode shape. This is our first mode shape for the frequency omega 1, which is equal to under root of k by m. Now what about the second mode shape? What about the second mode shape? So for the second mode shape, if mass m1 is going up, then mass m2 will be going in the opposite direction, which is down to the reference. While if mass m1 is going down from the reference, then m2 will be going above the reference. So this is the mode shape for the system when it is oscillated at the second natural frequency. This is known as the second mode shape with omega 2 as under root 3k by m. Okay, so if this is x1, this is minus of x1. This is x1, this is minus of x1. So these are the two mode shapes that we are going to encounter for our system. I hope this is clear and there is no doubt. So this is what the significance of a mode shape is. That is why we are concerned about the mode shapes, because then only we are going to know that how one mass is being linked to the other mass. See, here if we don't have the knowledge about how one mass is oscillating with respect to the other one, then how are we going to design our system? Suppose we have two masses and then we want to have the input, and input should be given in such a way such that the output is opposite to it for some time, and then it is supposed to be in sync with the input. So in that case, we can use the concept of mode shapes. Okay. So now we'll go to question number 5. Question number 5 is somewhat related to what we did in question number 4. The only difference is that there we discussed about a spring mass transport system, which is the translation system. Here we have the question about a torsional system wherein the rotation of this disk is happening. Okay, the rotation is rotating like this, not rotating fully actually, but it is encountering shear kind of behavior. So with this kind of system again, if we have the equation of motion, we can simply find the frequencies and mode shapes. Correct. So for this, if we have J1 as J theta, sorry, J naught, J2 as twice of J naught, yeah, and K torsional spring, kt2 as kt. Okay, and now when we are supposed to solve this, so see, for the first disk, which is like this, it is rotating like this by the angle theta 1. By the angle theta 1. Now, because of this, inertia is going to act, right? Okay, maybe I should just make a top view, that will be better. So, this is the disk, and it is rotating in the clockwise direction as theta 1. The inertia force is going to be like this, J naught theta 1 double dot. Then, if it is going in the clockwise direction, there will also be a spring force, right? Torsional spring is going to apply a resistive force or a restoring force in the opposite direction. So we'll have plus k t of theta 1. Other than that, because of the link between J1 and J2, this spring is also going to cause, going to apply a restoring force, whose value will depend upon the difference between the angular rotation between the disk J1 and J2. Okay, so it is going to be nothing but in this direction only, kt theta 1 minus theta 2. So finally we'll get J naught theta 1 double dot plus twice of kt theta 1 minus kt into theta 2 is equals to 0. This is the first equation. Second equation is going to be for J2. It is again going in the clockwise direction by theta 2. So inertia force will act as 2J naught theta 2 double dot plus, this time there is no torsional spring below J2. So only one is going to have the effect, and that one is because of the difference between the J1 and J2, angular deflection, difference of the angular deflection between J1 and J2. So it is going to be plus kt theta 2 minus theta 1. So final equation is going to be 2 J naught theta 2 double dot plus kt into theta 2 minus kt into theta 1 is equals to 0. So we can write it in the matrix form as J naught 0 0 twice of J naught theta 1 double dot theta 2 double dot plus twice of kt minus kt minus kt into kt theta 1 theta 2 is equals to 0 0. Now we are supposed to find out the frequencies. We know how to find out the frequency, correct? We assume theta 1 as theta 1 cos of omega t plus phi, theta 2 as cos omega t plus phi. Put it into the main equation. Put it into the main equation and get. Put it into the main equation and get. So I'm skipping the step that what are we going to get? We just have to find out the determinant, or we need to find out the equation such that the determinant minus j theta plus omega square plus 2 kt and minus kt minus kt minus 2 j naught omega square plus kt. Determinant of this equal to 0. Okay, we need to find out the solution for this. Now what we'll do, we'll multiply such that j naught omega square plus 2 kt into minus 2 j naught omega square plus kt plus kt square is equals to 0. This will give twice of j naught square omega to the power 4 minus kt j naught omega square minus 4 kt j naught omega square plus twice of kt square. Okay, here it should not be plus but rather a minus kt square is equals to 0. This can be further written as 2 j naught square omega to the power 4 minus 5 kt j naught omega square plus kt square is equals to 0. Again, we can assume omega dash as omega square, because of which it will become a quadratic equation, and then we can write omega dash 1 comma 2 as minus b 5 kt j naught plus minus under root of b square 25 kt square j naught square minus 4 into 2 8 j naught square kt square divided by 4 j naught square twice of a. This will give us 5 kt j naught plus minus 25 minus 8 is going to give us 17, I suppose. 17 under root of 17 kt j naught divided by 4 j naught square. So this is going to be 5 plus minus under root of 17 into kt by 4 j naught. So this is essentially what, 5. Anyways, it is going to be the plus part and minus part. Both are going to be less than, sorry, greater than 0. Okay, so under root of this is going to give us a the natural frequencies. So we are going to have the natural frequencies as omega 1 as under root of 5 minus under root of 17 divided by 4 kt by j naught, and omega 2 as 5 minus under root of 17 by 4 kt by j naught. These are the two natural frequencies linked to the system. Okay, one should be plus. Okay, yeah, that's fine. And the concerned mode shapes are going to be R1 as theta 2 by theta 1 of 1 as 2 minus 5 minus under root 17 by 4, and second one R2 is going to be theta 2 of 1 by theta 1 of, no, this 2 minus 5 plus under root of 17 divided by 4. So these are going to give us the mode shapes, right? From this we can find out how our modes are going to be when they are excited at any of the one of the natural frequencies. Coming on to question number 6. So we have again a 2 degree of freedom system. I suppose that till now you people are having a good understanding about how do we find out by looking at on the number of masses. that how many degrees of freedom the system is. So here we have a 2 degree of freedom system, and we have the values given as K1 as 30, K2 as 50, K3 as 0, M1 as 10, and M2 as 1. Anyways, the SI units are Newton per meter kg, and C are all 0. And we are supposed to find the free vibration response of the system. So this is a 2 degree of freedom system, and we have already worked upon a lot into how to find out the equation of motion. So I'm directly going to write the equation of motion, which is m1 x1 double dot plus k1 x1 plus k2 x1 minus x2 is equals to 0, and m2 x2 double dot plus k2 x2 minus x1 plus k3 into x2 is equals to 0. These are going to be the two equation of motions. Again, substituting, assuming the solution, substituting in this equation, and then finding out the value of determinant, we finally get the equation of determinant essentially as minus of m1 omega square plus k1 plus k2 minus k2 minus k2 minus m2 omega square plus k2 plus k3. Determinant of this should be equal to 0. Right, we have already done this. So essentially we just assume x1 as x1 cos of omega t plus phi and x2 as x2 cos of omega t plus phi. Then we put this in the main equation and get an equation in the matrix form. And then we have x1 and x2 on the right hand side, which is not going to be 0 always. So the only solution is if this coefficient matrix is 0. So we use it to find the natural frequencies. Now we put the values, then we are going to get minus of 10 omega square plus 35 minus 5 minus 5 minus of omega square plus 5, determinant equal to 0. This implies 10 omega square plus 35 minus omega square plus 5 minus 25 is equal to 0, which implies 10 omega to the power 4 minus 50 omega square. Then we have minus 35 omega square plus 175, I suppose, minus 25 is equals to 0. This will give us the form 10 omega to the power 4 minus 85 omega square plus 150 is equals to 0. Upon solving using omega square 1 comma 2, 85 plus minus under root of 85 square minus 4 into 10 into 150 divided by 20. The values of omega 1 and omega 2 are found as omega 1 as 1.5811 and omega 2 as 2.4495. So these are the two natural frequencies linked to the system. But in the question, we have to actually find out the response of the system, right? We are supposed to find out the free vibration response of the system, wherein we already have the initial condition of this form. So the initial condition we have x naught, x1 naught, okay, x1 of 0 is equals to 1, x1 of 0 dot 0, x2 of 0 is equals to 0, and x2 dot of 0 is also equal to 0. So these are the initial conditions that have been given, and we need to find out the free vibration response for this initial condition. So over here we were able to find out what? Only the Over here we were able to find out only the natural frequencies of the system. But in order to find out the free vibration response, so if you remember that it was discussed in the lecture also, that if my system is oscillating at any of the two natural frequencies, then at that time we'll have only one dominant frequency, or only both my masses are going to oscillate at that frequency. So suppose if I am oscillating given an initial condition to my system as this, which are whichever is linked to this mode for omega 1. So both my masses are going to oscillate with the frequency of omega 1, correct? Similarly, if I give the initial condition which is linked with the mode for the natural frequency omega 2, both my masses are going to oscillate with the frequency of omega 2. In that case, I can simply write the solution for both x1 and x2 in terms of any of the natural frequency, right? Like for the omega 1 mode, I can write x1 in terms of omega 1 and x2 also in terms of omega 1 because both are oscillating with the same frequency. Similar is for the case of mass m2 also. So what I'm trying to say is if my system is oscillating at any of the two natural frequencies, let us say omega I, then solution is going to be what? X1 cos of omega I t plus phi and x2 cos of omega I t plus phi, where omega I can be omega 1 or omega 2. Correct. This is how I can have my solution. But if you look in the question, we have an arbitrary initial condition which is not linked to any of the mode shapes that we are going to obtain for the natural frequencies. In that case, if you remember, it was discussed in the class that the solution of the system is going to be a summation, or it will be an addition of the two natural frequencies. I would like to bring a very basic concept that we learn in geometry, if you remember. For example, if I have the xy plane, and then here is a particle which is at a distance of 3 unit, this is 0, 0, on the x-axis, and at a distance of 7 unit on the y-axis. Okay, and I want to write it in the form of an equation. So how do I write it? In the vector form. I write it as 3i plus 7j, where I cap and j cap are what? These are unit vectors in the x and y directions. Now, I and j have the property that they are independent of each other, correct? Whatever my distance is on the x-axis is independent of what my distance is on the y-axis. These are two independent vectors that are used to give or to write the position of a particle on the xy plane, right? So what are we doing? We are writing the position vector of any point, let us say P, in the xy plane by the use of two independent unit vectors I cap and j cap. These both unit vectors are independent of each other. Clear? Similarly, for a two-dimensional system or for an n-dimensional system, we have the concept of eigenvalues and eigenvectors. So what happens is that, taking this analogy, that if I have two independent vectors, I can write the coordinate of any vector in the xy plane in terms of these two independent vectors. And these two vectors are not at all dependent on each other. They are independent. Similarly, for a two degree of freedom system, For a 2 degree of freedom system, or let us say okay, for now, let us say only for a 2 degree of freedom system, any solution X, any solution X1 of t, or we'll write it like this, any solution X can be written as, any solution X can be written as the linear combination of, can be written as the linear combination of, can be written as the linear combination of any two solutions. Linear combination of any two solutions. Now these solutions, capital X1 of t and capital X2 of t, can be dependent on each other or independent on each other. But if we have the independent solution, it is easier for us. Do you know why having an independent solution is easier for us? Because for the independent solution, our equation gets transformed into a decoupled one-dimensional equations. And we can simply solve it to get the solution. So for this case, if I have two solutions, capital X1 of t and capital X2 of t, I can find the linear combination of both and then I can write any general solution in that form. Okay. So for this, we try to find out the eigenvalues and eigenvectors. See, for a matrix, eigenvalue and eigenvector have a mathematical form, have a mathematical understanding. But when we take the concept of eigenvalue and eigenvector and put it over here for a system, planar system, physical system, if you'll see, we write the matrix, we use the matrix only to find the equation of motion. And I would like to give you the idea that if you will go and try to use the concept of eigenvalue and eigenvector to find out the eigenvalues and eigenvector definitely of the matrix that we are using, you are going to get the frequencies as well as the mode shapes. Why? Because then both the movement become independent of each other. Okay? They become independent of each other. From there comes the concept of eigenvalues and eigenvectors, right? That is what is the meaning of eigenvalues and eigenvectors, right? For a two-dimensional system, we find out the eigenvalues wherein what my equation becomes uncoupled, right? In these two directions, the motions are independent of each other. And if I get the solution in these two directions, I can simply make a linear combination of these both and write any general solution for my system, which is the basic concept that we use in the geometry as well. The same concept is used over here. And we use the concept of eigenvalues and eigenvectors or the concept of mode and mode shapes to find out the solution. I hope this is clear. Similarly, now when I use this concept in order to find out the general solution of my system, because here I am not oscillating with a particular mode, but rather I am giving it an arbitrary initial condition and I don't know how it is going to perform. But since I know the two natural frequencies, I know that there are two modes. Okay, I can use those concepts to what? To find out the general solution of my system, right? So for these two eigenvalues, when you will compute, you are going to get the mode shapes as xr of 1 as x2 of 1, x1 of 1 as 2, and xr of 2 as x2 of 2 divided by x1 of 2 minus 5. So in order to write any arbitrary general solution, I'll use the linear combination. I'll use the linear combination of what? Of the solution of my system at the natural frequencies, at the modes. Okay. So x1 of t can be written as x1 of 1. x1 of 1 can have any value and it will consider the value of the constant as well. Cos of, sorry, t plus phi plus x1 of 2 cos of 2.4495 t plus phi 1 phi 2. Okay. Here you see we have considered x1 of 1 as 1 constant and x1 of 2 as 1 constant. Okay. So what is essentially happening is that the first mode is going to have an amplitude of x1 of 1. Second mode is going to have an amplitude of x1 of 2. Okay. And because of the linear combination of these, we are going to have a solution for small x1. Similarly, for x2 of t, following the relation of mode shape, we can write as twice of x1 of 1 cos of plus, not plus, it should be minus 5 x1 of 2 cos of 2.4495 t plus phi 2. So this is the arbitrary solution. Simple. Using the same concept, we used two modes and the two mode shapes, and we wrote a arbitrary solution as a linear combination of these two. Okay. Now, since we already have the initial condition, if we use the values of the initial conditions that are given, we are going to have x1 at t0, which is equal to 1 as x1 of 1 cos phi 1 plus x1 of 2 cos phi 2, x1 dot of t 0, we have 0, which is 2 x1 of 1 cos phi 1 minus 5 x1 of 2 cos phi 2, x2 at t is equals to 0 is again 0, and it is going to be minus 1.5811 x1 of 1 sin phi 1 minus 2.4495 x1 of 2 sin of phi 2, and x2 dot at t is equals to 0, which is again 0, is going to be minus 3.1623 x1 of 1 sine of phi 1 minus, actually plus 12.2475 x1 of 2 sine of phi 2. So these are the four equations that we are going to get, and I've already solved this equation. So it will give us x1 of 1 cos phi 1 as 5 by 7 and x1 of 2 sine of phi 2 as 0. Okay, so okay, wait. First I'll write all the solutions for displacement, then we'll write for velocity. So x1 of 2 cos of phi 2 we'll get as 2 by 7. For the velocity, we are going to get x1 of 1 sine of phi 1 as 0 and x1 of 2 sine of phi 2 as 0. So from here we can see that phi 1 is equals to phi 2 is going to be equal to 0. So if phi 1 and phi 2 are 0, x1 of 1 is going to be 5 by 7 and x1 of 2 is going to be 2 by 7. Okay. So finally, using all this, we can write the final solution as x1 of t 5 by 7 cos of 1.5811 t plus 2 by 7 cos of 2.4495 t and x2 of t as 10 by 7 cos of 1.5811t plus 10 by 7 cos of 2.4495t. This is going to be the general solution of the system for the given initial condition. Last question, and we have, I guess, some time for it. Yes, we have 20 minutes. Okay, that's fine. Now, over here, I have taken a question of a car wherein we study the pitch and bounce motion. So, pitch motion is because of the rolling motion of the car, and then there is the bounce motion, which is because of the vibration of the car. Okay. Up till now, whatever question we were solving, we were mostly concerned about x1 and x2 or theta 1 and theta 2. We only did one question wherein there was a mass and then there was a pendulum. So the pendulum was oscillating with theta and mass was moving with x1. Over there also, but when we were supposed to find out the natural frequency, we converted theta in terms of x2 and then we used the linear like translation motion to find out the frequency. In this case, however, we have a rotation and then we have a oscillation translation. Both we have to consider. So it becomes a 2 degree of freedom system. The only difference is that here both are not translation or rotation. They are of different kind of nature. One is translation and other one is of rotation, theta. So we have to find out the frequencies. Definitely, if there are two kinds of oscillation, there is going to be two frequencies. Okay. In the first one, we like because of the bounce, we'll be considering the mass of the system. For the second, which is theta, we are going to consider the inertia of the system. Simple. So essentially, over here, the mass is only one. Unlike the questions that we have discussed till now, there were different masses. Okay. And depending upon the number of masses, we were finding out the natural frequencies and how many number of natural frequencies we have. Over here, that is not the case. We actually have one mass, but that one particular mass is having two different motions. One is the translation or bounce motion in the vertical direction, and the second one is the pitch, which is the rotational motion. And that mass only is showing the effect, one because one in terms of inertia and the second one in terms of the mass itself. So we are going to have a 2 degree of freedom system, and hence we'll be having two natural frequencies. Now for this system, we have an equation that we can use directly, but I'll go through some basic of that equation. So let us say that we have a rod like this. Okay, here we have its center of gravity. This is L1, this is L2, and these both are connected by spring like this. Mass and J theta. And this is K1, this is K2. Okay. Now, if I need to find out the equation of motion, see, if you remember, we actually did a question somewhat like this. Okay. I guess in the second or third week live session, wherein we were finding out the equation of motion and then the natural frequency. But what we considered over there was that the mass, like about the center of gravity, the rod was only rotating by a very small amount. We were not considering the translation, the coming down of the rod along with the rotation. Here we will consider the both. Okay. So from here, let us say that the rod is displaced in this way. Like this. So if we'll compare these both, This has come down by, let us say, x. Further, this is what? And this is what? Let us say that this is x2 and this is x1. How can we link x1 and x2? Let us say this is O, about which it is rotating, which is essentially the center of gravity, and this is theta. This is what we are calling as the pitch motion, correct? And the bounce motion is x. So we can write x1 in terms of theta. How? If this is L1, x1 is nothing but x minus L1 theta, and x2 is x plus L2 theta, correct? So if this spring is having a constant K1 and this is having a constant K2, what do we get? Mass is coming down by x. So inertia force is going to act in the upward direction. So we'll have m1 x1 double dot plus plus k1 into x minus L1 theta plus k2 x plus L2 theta. Correct? This is going to be equal to 0. Clear? About the spring force, I think it is clear. Both the spring forces are acting in the upward direction because both the springs are in compression state. So it will apply the force in the upward direction. Inertia is always is going to act in the upward direction, and so all will get added up. Next, if I consider about the rotation. Now, because of rotation, since it is rotating in the clockwise direction, we'll have the inertia in the anti-clockwise direction. So we'll have J naught theta double dot. The force due to K2 is in the direction of J naught theta double dot. So it is going to be positive plus K2 x plus L2 theta into L2 because we are considering the moment over here, right? And then the force because of K1 is making it rotate in the clockwise direction. So it will be negative. It will come with a minus. Minus K1 x1 minus L1 theta into L1 is equal to 0. These are the two equations. Again, we can write it in the matrix form. We can write it in the matrix form, which will give us m 0 0 j theta x double dot theta double dot plus k1 plus k2 minus of k1 L1 minus k2 L2 minus of k1 L1 minus of k2 L2 k1 L1 square plus k2 L2 square into x theta is going to be 0 0. So this is the matrix form that we got. Okay, it is applicable for the question that is already given to us. Okay, so if you remember, what were we doing when we were finding out the frequency? We were assuming the solution. So we'll assume x as capital X cos of omega t plus phi and theta as cos of omega t plus phi. Put it in the equation and then write it in the matrix form. And then from there, what we are going to get? We are going to get the relation such that minus m omega square plus k. See, it is going to be k1, k2. Here we have k1 as kf and k2 as kr. So we'll write it in terms of that only because eventually then we have to put the values of kf and kr. Kf plus kr. Then we'll have a minus kf into L1 plus KR into L2. Over here we'll have minus of KF L1 plus KR L2 minus of J naught omega square plus Kf L1 square plus Kr L2 square. X theta. Again, this will not be equal to 0. So determinant of this thing should be equal to 0. Putting the values given in the question, comma, what do we get? So I've already written it. We'll get minus 1000 omega square plus 40,000, 15,000, 15,000 minus 810 omega square plus 67500. Instead of writing it in the matrix form, we just write its determinant should be equal to 0. Okay, this will give us 1000 omega square plus 40,000 into minus 810 omega square plus 67500 minus 15,000 square is equal to 0. After doing all the calculations and eliminating some zeros, we'll get 8.1 omega square, not omega square, omega to the power 4 minus 999 omega square plus 24750 is equal to 0. From this, we are going to get omega 1 as 5.8593 radians per second and omega 2 as 9.4341 radians per second. Okay, I hope this is clear. So one is going to be the frequency because of bounce, and the other is going to be the frequency because of pitch. I hope this is clear. So these are going to be the two frequencies. What is interesting in this question over here is that earlier we were having multiple masses, and depending upon the number of mass, we were saying that okay, number of mass is going to be equal to the number of natural frequencies that we are going to get, number of degrees of freedom, and the number of equations. Over here, we have a single mass, we have a single center of gravity. But apart from that, what do we have? We have two kind of motion. One is because of translation, other is because of rotation. Now that single mass is going to show effect as mass for translation and as inertia for rotation. So a single mass is present over here, but then the system becomes a 2 degree of freedom system with two natural frequencies just because of the fact that the same mass, the same car, along with bounce, it is also encountering pitch motion. Okay, I hope this is clear to you all. So yes, this is it for today's live session. So I tried covering the questions which will be helpful for you to solve the assignment problems. The assignment problems are easy, I suppose. I have, in fact, I've discussed tougher questions in the live session. Mm, I hope you people will be able to solve the assignment problem. So, okay, thank you so much for attending the live session, and we'll meet next week, Tuesday, 6 p.m. again for the week 8 live session. If anyone has any question, they can ask, or I'll end the meeting. Okay, I suppose no one has any question, so I'll end the meeting now. Thank you so much for attending.